What if our most advanced theories about the universe are not entirely our own? Imagine for a moment that they were seeded into our collective imagination by a civilization so ancient and powerful it exists outside the very fabric of our reality. They might tell a story not of a Big Bang, but of a cosmic tragedy, a tale where their own higher dimensional universe was consumed by an unimaginable entity, a black hole, which in turn gave birth to ours. This is not just a flight of fancy. It's a speculative theory suggesting we are living inside the aftermath of a cosmic cataclysm. If this account holds any truth, then the universe we call home is the byproduct of a phenomenon far stranger than we have ever been told, and our entire understanding of existence might be based on a profound misunderstanding. The pull of black holes is magnetic. They are among the most profound puzzles in the cosmos. These invisible domains of space-time are compelling not just for their supreme gravitational power, but for the way they test our basic grasp of reality. The evolution of black holes from theoretical curiosities to essential elements of modern cosmology is a story filled with intellectual twists as captivating as the objects themselves. Their importance lies not only in their gravitational effects on stars and galaxies, but also in their deep influence on human thought and our quest to comprehend the universe. The intellectual journey toward understanding black holes began long before the term existed, stretching back to the 18th century. It was then that a British clergyman and natural philosopher, John Michell, first speculated about the possibility of dark stars. He proposed that a star could be so extraordinarily dense that its gravitational influence would become powerful enough to ensnare light itself, preventing it from escaping. Michell, of course, didn't call them black holes, nor did he possess the technology to prove his hypothesis. Even so, his imaginative thinking provided the foundational concepts upon which later scientists would build. For a long time, Michell's ideas were viewed as little more than intellectual curiosities. It would be almost 200 years before science would revisit these notions with serious consideration. Leaping forward to the dawn of the 20th century, Albert Einstein's theory of general relativity completely transformed our view of gravity. Rather than seeing gravity as a simple force, Einstein revealed it as the curvature of space-time. Very large objects, like stars, actually bend the fabric of space, and smaller bodies simply follow these curves. This fundamental change in perspective created the theoretical framework for black holes to exist. Einstein himself was skeptical of the concept. He struggled with the idea that nature would allow for such bizarre cosmic objects to form. Yet mathematics doesn't bend to personal belief. In 1916, when Carl Schwarzschild provided a solution to Einstein's equations, he uncovered something extraordinary. Under the right conditions, a star could collapse into a point of such incredible density that it would forge a gravitational chasm, which we now call a black hole. Schwarzschild's breakthrough was a remarkable intellectual feat, but it was largely unnoticed amid the turmoil of World War I. He developed his work on these challenging equations while serving in the German army, frequently under dangerous conditions. Despite the difficult environment, his calculations offered scientists a new way to perceive the universe. Schwarzschild's work did more than just describe the potential for black holes. It also defined their boundaries, which are now known as event horizons. This is the ultimate point of no return. Anything that ventures across this line, light included, is forever trapped. Even with Schwarzschild's visionary discoveries, black holes were considered a scientific oddity for decades. A great number of scientists remained doubtful about their actual presence in our universe. Einstein himself consistently expressed his disagreement with the concept, dismissing them as gross misinterpretations of his own theories. It was not until many years later, when astronomers started finding signs of strange objects in the cosmos, that the reality of black holes began to seem credible. The identification of Cygnus X1 during the 1960s marked a crucial turning point. This was a binary system in which one star seemed to be orbiting a partner that was completely invisible. This mysterious nothing was ultimately confirmed to be a black hole, becoming the first of its kind to be broadly accepted by the scientific world. What makes black holes all the more intriguing is their significant impact on our perception of space and time. In the immediate area of a black hole, time itself experiences a significant slowing. This is not just a theoretical idea, it's an observed effect in zones of powerful gravity. In such places, clocks would literally tick more slowly. If you could somehow stay near a black hole and look back at Earth, you would see time on our planet speeding by much faster than it was for you. This warping of time and space is more than a scientific curiosity. It is a primary reason some researchers think black holes could unlock some of the universe's deepest secrets. However, black holes are not confined to the world of science. They have also deeply fascinated artists and authors. Poets and fiction writers were imagining cosmic voids long before there was scientific evidence to support their existence. In his poem Eureka, Edgar Allan Poe described a universe collapsing into itself. While his vision isn't scientifically precise, it shares a certain resonance with the modern idea of a singularity. Drawing inspiration from Einstein's theories, surrealist artists like Salvador Dalí wove ideas of infinity and warped reality into their work. By the 20th century, black holes had become powerful cultural symbols of both terror and wonder. The name black hole itself didn't come into use until 1967, when it was introduced by the physicist John Archibald Wheeler. Before that, these objects were known by other names like frozen stars or dark stars. The new name caught on with the public in part because it perfectly captured the air of mystery that surrounded these cosmic phenomena. Movies such as Disney's The Black Hole and more recent films like Interstellar turned these cosmic puzzles into key story elements, merging scientific principles with creative narrative. And yet, even as black holes entered everyday language, the science explaining them remained incredibly intricate and, in some ways, hard to grasp. It's a common misconception that black holes are just passive cosmic vacuum cleaners. In reality, they are dynamic objects that actively draw in and devour anything that comes too close. As material gets pulled toward a black hole, it creates a swirling ring of gas and debris called an accretion disk. When these disks heat up enough, they radiate powerful X-rays that can be seen by telescopes on Earth. Another distinct feature of these objects is the formation of jets, which are powerful streams of energy that get shot out from the black holes at almost the speed of light. These jets can stretch for thousands of light years and have a major influence on the evolution of galaxies and the way matter is spread across the universe. The link between black holes and the grander architecture of the cosmos is a key reason scientists take them so seriously. Supermassive black holes like the one found at the center of our Milky Way galaxy, Sagittarius A, have a vital function in shaping their cosmic neighborhoods. These celestial titans can have masses that are millions or even billions of times larger than our Sun, yet they exist in a space no bigger than our own solar system. It is their immense gravitational force that binds entire galaxies together. It's unclear if galaxies, and therefore life as we know it, could even form without them. Not every culture has seen black holes or similar ideas as omens of destruction. In Hindu cosmology, for example, there is a belief in perpetual cycles of creation and annihilation. Certain readings of these ancient stories align remarkably well with contemporary scientific thought. The cosmic dance of Shiva, which symbolizes the universal cycle of creation and destruction, has interesting parallels with how black holes consume matter and then redistribute it through powerful jets. Indigenous cultures also have stories about light eaters or cosmic abysses, which suggests that people have long tried to make sense of phenomena that are beyond our direct experience. Black holes are compelling for reasons that go far beyond their cultural significance. They also represent the limits of our scientific understanding. At the very center of a black hole, where density is believed to be infinite, we find one of the biggest puzzles in the universe, the singularity. In this tiny region, our current laws of physics simply fail. The very ideas of space and time lose their meaning. Some physicists theorize that if we could understand what a singularity truly is, we might learn about the origins of the cosmos itself. The Big Bang may have been a singularity, the event that marked the beginning of our universe from an incredibly dense and hot point. The ways in which black holes connect to other cosmic events are even more captivating. Quasars, which are the brightest objects known in the universe, are fueled by supermassive black holes. The study of quasars has given us great insight into how these powerful objects work. Black holes serve as the engines that drive quasars, which can generate more light and energy than entire galaxies. This paradoxical quality of black holes, being both destroyers and creators, is a big part of why they continue to hold the fascination of both scientists and the public. Modern technology has given us a much closer view of black holes. The Event Horizon Telescope, which is a worldwide collaboration of observatories, succeeded in taking the very first picture of a black hole in 2019. This image of the supermassive black hole in the M87 galaxy was more than just a scientific success. It was a major cultural moment. For the first time, we could actually see the shadow of a black hole, which was encircled by the bright, glowing ring of its accretion disk. This discovery confirmed many of the predictions made by the theory of general relativity, but it also brought up new questions. What is hidden beyond that shadow? Could these mysterious regions contain clues about the universe's hidden dimensions? The notion that our own universe could be located inside a black hole is not as unbelievable as it might first seem. Certain scientists suggest that black holes in a higher dimensional space could generate new universes within them. This theory is related to the holographic principle, which posits that everything we perceive in 3 dimensions might actually be a projection from a 2-dimensional surface. According to this perspective, black holes are not merely cosmic curiosities. They are potential gateways to grasping the fundamental fabric of reality. This link between black holes and the universe's overall structure has been strengthened by the observation of gravitational waves. These ripples in the fabric of space-time, which were first detected in 2015, are frequently produced by the collision of black holes. Observing these waves gives scientists a brand new method for listening to the universe. Each detection provides further proof of the strange and interconnected nature of black holes and the cosmos. Although we still don't have all the answers, it's becoming apparent that black holes are much more than just areas of space where gravity is all-powerful. They are fundamental to understanding everything from the creation of galaxies to the possible fate of the universe. Whether they contain the secrets of other realities or just show us the current limits of our knowledge, they continue to be among the most mysterious and alluring objects in the cosmos. Albert Einstein's theory of general relativity permanently changed how we see space, time, and gravity. Before his work, gravity was understood as a force that acted between two different objects, like the Earth and the Moon. Einstein's concept was groundbreaking. He suggested that gravity isn't a force at all, but is instead the bending of space-time created by the presence of mass. Heavy celestial bodies like stars or planets make dents in the fabric of space-time, and other objects simply travel along these dips. You can think of it like putting a bowling ball on a stretched-out rubber sheet. The ball makes a curve and smaller marbles roll toward it. This new way of understanding gravity wasn't just a theory. It explained many things about how the universe works, and one of its most intriguing predictions was the existence of black holes. Black holes were not instantly recognized as real phenomena when Einstein presented his equations in 1915. He himself had reservations about their existence. The concept seemed far too strange. Areas of space where gravity is so powerful that nothing, not even light, could get away. But Einstein's mathematical formulas were clear. In 1916, Carl Schwarzschild was the first to find a solution to these equations for a particular situation. His solution showed that under extreme circumstances, if a star was massive enough and collapsed under its own gravity, it could create a point of infinite density, a singularity. This singularity would be surrounded by an unseen border, which was later named the event horizon. Anything that passed this boundary would be lost forever, with no chance of return. Schwarzschild's discovery was revolutionary, but it was largely ignored because of the chaos of World War I. He worked on his equations while he was serving in the German army and did not survive to see their full influence. Nonetheless, his work established the groundwork for our current understanding of black holes. The event horizon is a critical characteristic of black holes. It isn't a solid surface like the ground you can stand on. Rather, it is a mathematical border. If you get too close to it, the escape velocity, the speed you need to get away from the gravitational pull, becomes faster than the speed of light. Because nothing can go faster than light, nothing can escape once it crosses this line. Inside the event horizon, the physics we know no longer applies. Time and space are warped so much that they almost lose their meaning. At the very center of the black hole is the singularity, where density becomes infinite, and the curvature of space-time also becomes infinite. The event horizon hides the singularity from the rest of the universe, which is why we can't see it directly. Some scientists even wonder if singularities truly exist, or if they are just a sign that our understanding of physics is not yet complete. Not every black hole is the same. They are found in various sizes and forms. Stellar black holes come into being when huge stars collapse at the end of their lives. These black holes usually have a mass that is a few times greater than that of our Sun. Then there are supermassive black holes, which are millions or even billions of times more massive than the Sun. These colossal objects are found at the centers of most galaxies, including our own Milky Way, which hosts a supermassive black hole known as Sagittarius A star. There are also intermediate black holes, which are smaller than supermassive ones, but bigger than stellar black holes. These are harder to locate and are believed to be formed through the merging of smaller black holes. Finally, there are primordial black holes, which, if they are real, were created in the early moments of the universe. These tiny black holes might even be the key to explaining the nature of dark matter, the enigmatic substance that makes up most of the universe's mass. The specific properties of a black hole can also determine its actions. A Kerr black hole, which is a type of spinning black hole, actually pulls space-time around with it as it rotates. This effect, called frame dragging, has been confirmed by experiments like Gravity Probe B. Another kind is the electrically charged black hole, which is also known as the Reissner-Nordstrom black hole. While they are theoretically possible, charged black holes are very unlikely to be found in the real world because most objects in space are electrically neutral. One of the most remarkable aspects of black holes is their ability to release energy. Even though nothing can get out from beyond their event horizon, black holes are not completely dark. As matter is pulled toward a black hole, it creates a swirling ring of gas and dust called an accretion disk. When the material in this disk heats up to millions of degrees, it gives off radiation, including X-rays, that can be seen from Earth. In addition, some black holes shoot out incredibly powerful jets of energy that launch particles away at nearly the speed of light. These jets, which can be thousands of light years long, have a major impact on the formation of stars and galaxies. Time seems to slow to a crawl when you are very close to a black hole compared to places that are farther away. This effect, known as time dilation, is not just a theory. We have seen very similar results in experiments here on Earth. For instance, the rate at which a clock ticks slows down as the strength of the gravitational field increases. This effect is most extreme near a black hole. If you were to hover just outside the event horizon, time would seem to stand still for you, and you would see the rest of the universe speeding up around you. The investigation of black holes has also advanced our knowledge of other cosmic events. For example, quasars, which are among the most luminous objects in the cosmos, are driven by supermassive black holes at the centers of galaxies. These black holes draw in vast quantities of gas and dust, and the energy that is liberated in this process can be brighter than entire galaxies. Quasars serve as a powerful illustration of how black holes, which are often seen as agents of destruction, can also be tremendous sources of energy. Black holes also have a connection to the expansion of the universe. The observation of gravitational waves, which are ripples in space-time created by the collision of massive objects, has given us direct proof of black hole mergers. These waves were first observed in 2015 by the LIGO Observatory and have since turned into a crucial instrument for investigating black holes. Each new detection not only validates Einstein's theories, but also helps researchers learn more about the most extreme events in the universe. Hawking radiation, a theory put forth by Stephen Hawking, introduces another level of intricacy to our comprehension of black holes. Based on quantum mechanics, black holes are not entirely black. They gradually lose energy through a mechanism that involves virtual particles appearing near the event horizon. Over an immense period of time, this loss of energy makes the black hole shrink and eventually disappear. Although Hawking radiation has not been directly observed yet, it holds significant implications for our understanding of black holes and the fundamental laws of physics. Some scientists also theorize that black holes might be linked to other regions of the universe through wormholes, which are hypothetical passages connecting different points in space-time. These concepts are purely theoretical at this point, but they open up exciting possibilities about the nature of reality and the structure of the cosmos. The holographic principle, another theoretical idea, posits that everything inside a black hole might be recorded on its event horizon. This concept has inspired new ways of considering information, entropy, and the universe as a whole. Black holes are not just subjects of scientific fascination, they are vital to comprehending the universe. From their creation to their influence on shaping galaxies, they push the limits of our understanding of physics and what we know about space and time. Whether it's through their immense gravitational force, their capacity to bend light, or their enigmatic singularities, black holes continue to fascinate scientists and the public. String theory introduces a remarkable idea. Our universe might have more dimensions than the three we are used to. In this theoretical model, there could be as many as 10 or even 11 dimensions, but these extra dimensions are hidden from our view. They are so incredibly small and curled up that we don't see them in our daily experience. They aren't like length, width, or height, but exist on a completely different scale. These hidden dimensions are essential to string theory, and the mathematical framework doesn't work without them. When scientists talk about the idea of a universe inside a black hole, these extra dimensions are a key part of the puzzle. In brain cosmology, a model that comes from string theory, the universe we know is just one part of a much larger structure. According to this theory, our universe is a brain that floats in a higher dimensional space, often called the bulk. We are like a sheet of paper within this bigger space, and there could be other brains nearby. In this view, black holes might be the connections between these brains or even pathways to other dimensions. Gravity, for example, might be weaker than other fundamental forces because some of it escapes from our brain into the bulk. This idea could explain why gravity seems so much weaker than forces like electromagnetism or the nuclear forces. Scientists wonder if black holes might be higher dimensional objects themselves. If we were able to see them from a higher dimensional viewpoint, they might not look the same as they do in our three-dimensional space. In our universe, black holes look like points of infinite density with event horizons around them. But in higher dimensions, they could have much more intricate shapes, like spheres or other forms, and their characteristics might be different. Some theories propose that black holes in higher dimensions could pinch off parts of space-time, creating something entirely new, a process that could even result in the birth of a new universe. M-theory, which is a more developed version of string theory, expands on these ideas even more. It suggests that to understand everything in the universe, we need to consider 11 dimensions. This theory brings together all the known forces, including gravity, electromagnetism, and the forces that bind atoms. In M-theory, black holes are not just three-dimensional points, but could be higher-dimensional objects known as black brains that stretch across several dimensions. These black brains could influence not only our universe, but also other dimensions or universes at the same time. Some scientists believe that the creation of our universe might have been the result of a black hole collapsing in a higher dimension, with the Big Bang being the outcome. This leads us to the black hole universe hypothesis, which posits that the conditions within a black hole might be similar to those of a Big Bang. Think about all the matter and energy inside a black hole being squeezed to a point where space and time no longer function. Some scientists suggest that this incredible compression could trigger the creation of a new universe with its own unique rules and structure. The event horizon of a black hole could serve as a border between universes. Just as we can't see past the edge of our own universe, nothing can get out from beyond the event horizon. In both situations, it's a boundary that separates different worlds. Some features of our own universe might support this idea. When scientists examine the cosmic microwave background, which is the faint radiation left over from the early universe, they notice patterns that are hard to explain. A few scientists believe that these patterns could be remnants from a black hole's collapse if our universe was formed inside one. If we are living inside a black hole, it could be why we can't find an edge to our universe. Just as the event horizon hides what's inside a black hole from our sight, our universe might have a similar boundary that we can't look past. The holographic principle is another key element in this puzzle. It proposes that everything we see in 3 dimensions is actually recorded on a 2-dimensional surface. This idea first came from studies of black holes. Researchers discovered that the information about what goes into a black hole seems to be kept on its surface, not inside it. If this is correct, then our reality might be a kind of projection, with everything inside a black hole represented on its outer boundary. In this perspective, black holes are not just cosmic vacuums. They are information-storing devices that hold details about their parent universes. The peculiar link between black holes and the universe extends even further. Some scientists theorize that black holes could help us understand why the universe is expanding at an accelerating rate. Dark energy, the enigmatic force behind this acceleration, might originate from interactions with something outside our universe. If our universe is within a black hole, then the parent universe could be exerting a pull on it, leading to expansion. This would mean that the accelerated expansion we see is not just a feature of our universe, but a consequence of its connection to a larger cosmic structure. This black hole hypothesis is also connected to the laws of thermodynamics, particularly the second law, which says that entropy or disorder always tends to increase. Black holes also possess entropy, which is determined by the surface area of their event horizon. This discovery was a surprise to scientists because it points to a link between black holes and space-time itself. It also supports the holographic principle, where the surface area, rather than the volume, contains all the information. If our universe is inside a black hole, its entropy might be stored on a two-dimensional boundary, offering a new way to think about the structure of reality. The behavior of time is also strange within a black hole. As things get closer to the event horizon, time slows down compared to an observer outside. This effect, known as time dilation, might give us a clue as to why our universe's expansion seems to be speeding up. From inside a black hole, time and space could be warped in ways that make the expansion appear faster. This idea connects to the black hole universe hypothesis, where the passage of time inside a black hole is different from the passage of time outside it. These concepts don't just apply to black holes in our own universe, they also extend to black holes in other universes, if they exist. In M-theory and brain cosmology, black holes can affect multiple universes or dimensions. They might serve as anchors or nodes that connect different parts of the multiverse. Some researchers even believe that black holes could produce baby universes, which are smaller regions of space-time that branch off from a larger universe. This branching would mean that black holes are like cosmic seeds that grow new universes inside them. Quantum gravity, which is the effort to merge quantum mechanics with general relativity, also uses black holes as a testing ground. Some quantum gravity theories propose that black holes contain quantum seeds that could develop into new universes under the right conditions. These seeds could hold the initial conditions for a universe, providing a template for how it might evolve. The Planck scale conditions near a black hole's singularity, the region of highest density and smallest scales, could be similar to the conditions at the beginning of our own universe, which supports the idea that black holes create new realities. Even observational data suggests that something unusual is happening on the largest scales. Dark energy, which constitutes most of the universe's energy, might be a kind of force or energy transfer with the parent universe outside the black hole. This transfer would act like a cosmic push, causing our universe to expand from within. Black hole thermodynamics, which examines the temperature and entropy of black holes, also offers some hints. The entropy of a black hole is proportional to the area of its event horizon, not its volume, which suggests that the structure of space-time could be deeply connected to black holes. The ideas that connect black holes to other universes might seem complicated, but they paint a fascinating picture of how the universe could function. They suggest that black holes are not just points of infinite gravity, but are instead crucial components in a much larger cosmic framework. This perspective challenges the conventional Big Bang theory as a single event, proposing instead that our universe could be one of many, created in a multiverse teeming with black holes. Imagine a cosmos where your decisions can actually create new realities. Instead of going right, you go left. In one reality, you make a certain choice. In another, you skip lunch. When these small changes are multiplied across an endless number of possibilities, you get a vast multiverse. Although it might seem like something out of science fiction, the idea of parallel worlds actually comes from quantum physics, which suggests that particles can be in multiple states at once. Some scientists are now thinking that black holes might be the key to these parallel universes. One theory proposes that every universe is like a bubble in an endless sea of universes. Each bubble is formed when a new universe comes into being, often with its own distinct laws of physics and fundamental constants. Are these universes completely cut off from ours, or could black holes serve as bridges between these bubbles, linking them with their powerful gravitational forces? The idea is that black holes might connect universes, enabling energy, matter, or even information to move between them. In this way, black holes would be gateways, joining what we once thought were separate worlds. In a different version of the multiverse known as the brain theory, our universe is just one three-dimensional brain floating in a higher dimensional space called the bulk. You can think of it as a sheet of paper drifting in a larger room, with other sheets of paper floating nearby. If black holes exist on these brains, they might forge connections between them. These connections would be hidden from our view, but they could allow energy or gravity to pass from one brain to another. This could explain why gravity feels so weak in our universe. It might be leaking into other brains through black holes. Once something passes the event horizon, it's gone forever, isn't it? But what if there's more to the story? Some scientists propose that the singularity inside a black hole could be connected to a white hole in a different universe. A white hole would be the reverse of a black hole, pushing matter out instead of pulling it in. If this link exists, it would mean that anything that falls into a black hole in our universe might come out in a different form somewhere else. This connection might not be visible from outside the black hole, but it could mean that black holes are more than just cosmic destinations. They might be points of exchange, where universes interact in ways we can't yet fully grasp. Wormholes, often thought of as shortcuts through space, could also be involved here. Some researchers believe that black holes might keep wormholes stable, creating bridges not just through space, but across different universes. If these wormholes do exist, they wouldn't be easy to pass through. The energy needed to hold them open would be immense, possibly taken from the spin of the black hole itself. And they might not connect 2 points in our universe, but instead link different universes, creating a network where black holes serve as transit points between realities. To keep a wormhole stable, scientists think you would need something called exotic matter, which has negative energy. This exotic matter doesn't exist in our normal world, but in theory, it could keep a wormhole open, making it possible to travel through. Some physicists believe that at very small scales, black holes might contain tiny quantum wormholes that connect to other universes on a quantum level. These small wormholes could form an unseen web that connects not just galaxies, but entire universes. If black holes do connect universes, it would completely change our concept of reality. Instead of a single self-contained universe, we might be part of a network where each universe is linked to others, with black holes acting as cosmic passages. This would mean that our universe is not alone, but is part of a complex web, and black holes are central to this system. It also challenges our idea of boundaries. If black holes are portals, there might not be a real edge to our universe. Instead, each black hole could open into an entirely new world. Black holes might take in matter and energy from one universe and transfer them to another. This would make black holes more than just endpoints. They would be cosmic recycling plants, deconstructing matter in one universe and reforming it in another. If black holes permit energy to move between universes, it could also provide an explanation for some of the puzzles in our own universe, like dark energy, the force that pushes everything apart at an accelerating rate. Some scientists suggest that this expansion could be affected by forces from other universes interacting with ours through black holes, gently pushing everything outward. This concept also relates to the black hole information paradox. In classical physics, information is never really lost. But when something falls into a black hole, it seems as if the information about it is gone. This confuses scientists, who wonder if this information somehow moves to another universe instead. If black holes are portals, the information could be saved, just in a different form, in a different universe. This would mean that what we perceive as lost could just be crossing a boundary we don't yet understand. The laws of quantum mechanics and relativity are both relevant here. Quantum entanglement, a phenomenon where particles stay connected even when they are far apart, might suggest a hidden link between black holes in different universes. This could mean that black holes are not just separate objects, but are part of a vast, interconnected system. When two black holes merge, they emit gravitational waves, ripples in space-time that travel across the universe. Some scientists believe these waves might even carry signals from other universes, leaving faint traces that we could one day find. If this is true, every black hole merger could tell us more about the structure of the multiverse. There are other hints as well. When scientists look at the cosmic microwave background, the faint radiation left over from the early universe, they sometimes see patterns that are hard to account for. Some think these patterns could be signs of interactions with other universes, possibly through black holes. And then there are gamma-ray bursts, powerful flashes of energy that seem to originate from distant galaxies. These bursts are so strong that they bring up questions about their sources. Some scientists wonder if they might be signals from high-energy events that involve black holes in other universes. Even Hawking radiation, the slow emission of energy from black holes, might hold clues about other worlds. If the radiation patterns from a black hole don't fit our expectations, it might indicate that something unusual is happening, like energy seeping in from another universe. Observing these discrepancies could give us hints about what is beyond our own universe. All of these theories come with big questions. If black holes are actually portals, what happens to things that cross the event horizon? Are they destroyed, or do they reform in another universe? If black holes connect universes, it goes against the long-standing belief that nothing can escape. Some scientists believe that black holes might be one-way passages, allowing matter to flow in only one direction. Others wonder if some black holes could let energy travel both ways, creating a bridge that allows energy and perhaps even information to move back and forth. The idea of black holes as gateways to other universes is not just a fantasy. It's a way of looking at the universe that challenges what we know and encourages us to imagine what might be out there. If black holes really are portals, they might hold the secrets to a multiverse more vast and complex than anything we've ever imagined. Each black hole could be a doorway, and each doorway could lead to a reality as real as our own, yet forever hidden on the other side of the stars. Einstein's field equations might seem abstract, but they are the foundation of our understanding of black holes. They don't just give us numbers, they show how space and time twist, bend, and stretch under extreme gravity. These equations are complex, 10 interconnected differential equations that link mass, energy, and the curvature of space-time. When Einstein released them in 1915, he probably didn't imagine their future uses, but today they are essential for understanding black holes. The complexity of these equations becomes clearer when scientists apply them to black holes. Under certain conditions, the equations predict that space-time can collapse into a point with infinite density, creating what we call a black hole. Carl Schwarzschild was the first to find a solution to these equations for a simple black hole, one that is non-rotating and perfectly spherical. This solution, called the Schwarzschild solution, defines the event horizon and predicts how light and matter would act near it. However, real black holes are rarely this simple. They spin, they interact, and they collide with each other, which requires more complex solutions and, more often than not, the help of computers. For rotating black holes, the Kerr solution adds another level of intricacy. It describes how a black hole's spin warps spacetime, creating a kind of cosmic whirlpool where space itself is twisted. This effect, known as frame dragging, is so strong that it distorts everything around the black hole, including light. The equations that describe this rotation are much too complex to be solved by hand, so scientists use computers to run simulations that show these dynamics in detail. Creating a black hole simulation is more than just entering numbers into a computer. Each black hole is divided into tiny pieces, like a grid laid over space-time. Scientists calculate the gravitational pull on each point of this grid based on the points around it, updating these positions with every passing moment. This method is called numerical relativity, where computers do the massive calculations needed to keep up with Einstein's equations in real time. One method, called finite difference, uses the grid to break down the differential equations into smaller, more manageable parts. By tracking how space-time changes at each part, researchers can build a picture of a black hole's actions over time. Another method, adaptive mesh refinement, focuses computing power on key areas, like the event horizon. This technique is crucial when dealing with complex phenomena like black holes because it improves accuracy without overloading the system. When it comes to black hole mergers, simulations must handle incredible gravitational forces. The collision of two black holes is one of the most powerful events in the universe. As they get closer, they send out gravitational waves, which ripple through space-time, like waves on a lake. These simulations have to track every twist and turn, showing how the black holes spiral toward each other and finally merge. After the merger, there's a ring-down phase where space-time shakes and slowly calms down, sending out specific frequencies called quasi-normal modes that scientists can detect with instruments like LIGO and Virgo. These black hole mergers are not just theoretical. The patterns in the gravitational waves match the predictions from simulations, which confirms that we're on the right track with these models. LIGO's observations of merging black holes in 2015 made the theory real, and each new detection improves our understanding of black hole behavior. Even the recoil, or kick, from merging black holes, where the new black hole is pushed away from its original spot, has been simulated and observed, giving us insights into how these massive objects interact. Simulating black holes demands immense computing power. Supercomputers like Blue Waters and Summit process billions of calculations every second to recreate black hole dynamics. Some simulations take weeks or even months to run, with scientists using parallel processing to divide the calculations among hundreds or thousands of processors. It's a process that requires time, energy, and patience, but the results give us a look into the hidden workings of these cosmic giants. Even light acts differently near black holes, and simulations help us to understand these strange effects. Geodesic tracing, a method that follows the path of light around a black hole, lets scientists model how photons loop and bend in the black hole's gravity. The outcome is a photon ring, a bright circle around the black hole, where light orbits multiple times before either escaping or being captured. This photon ring is what we see in the famous Event Horizon Telescope image of the M87 black hole. The ring isn't the event horizon itself, it's light being bent by the black hole's gravity, an effect that simulations predicted and the EHT confirmed. The Event Horizon Telescope, EHT, uses a method called interferometry to merge data from telescopes all over the world. By combining light from each place, the EHT creates a global network with a resolution sharp enough to photograph black hole shadows. The data is processed with sophisticated algorithms to reconstruct black hole images, allowing us to see the shadows cast by the event horizon. This visual information matches simulation predictions, helping scientists to check their models with actual observations. But the simulations do more than just create images. They also give us other insights, like how black holes form accretion disks. These swirling rings of gas and dust heat up as they spiral toward the black hole, reaching millions of degrees. Simulations show that these disks are extremely turbulent, with particles crashing into each other at high speeds. The energy from these collisions creates X-rays, which astronomers can detect with space telescopes, giving us a view into the extreme environment around black holes. In addition, simulations demonstrate that black holes possess the capability to emit highly powerful particle jets that can travel from their poles at nearly the speed of light. The black hole's rotation twists the magnetic fields, which in turn release particles in enormous streams, forming these jets. These jets, which can span thousands of light years in the case of supermassive black holes, influence the formation of stars and potentially entire galaxies. The mathematics behind these simulations poses special challenges, especially near the singularity, where density becomes infinite. Standard calculations fail here, so scientists use techniques like excision, where they cut out the singularity from the grid to prevent undefined results. This method allows simulations to concentrate on the event horizon and nearby areas where most observable effects happen. Coordinate transformations also help to make the math simpler. By altering how distances and directions are measured, scientists can model black holes using coordinates that make calculations easier. Spherical and polar coordinates are frequently used as they fit better with a black hole's shape than standard grid systems. Each of these adjustments helps the simulation to run more smoothly and precisely, getting us closer to a true picture of black hole behavior. The dynamics within a black hole show strange effects, like the warping of the event horizon. Simulations reveal that black hole event horizons aren't perfectly even. They can develop bulges or twists because of strong gravitational interactions, especially in black hole mergers. These distortions affect the light and matter nearby, bending them in unique ways. As black holes spin, they create frame-dragging effects, twisting space-time around them. This effect, predicted by relativity and confirmed through simulations, is particularly strong in fast-spinning black holes. These frame-dragging zones pull in nearby matter, creating a sort of cosmic whirlpool around the black hole. These simulations have also verified that merging black holes create specific, gravitational wave patterns, or tones, much like a musical instrument. These frequencies, known as quasi-normal modes, are determined by the black hole's mass and spin, which allows scientists to figure out these properties from gravitational wave data. It's like reading a black hole's signature written in the ripples of space-time. Simulations show that black holes with high spin can twist space-time into complex patterns, affecting how nearby particles move. These rotations pull material along with them, creating a special kind of turbulence in the accretion disk. Matter heated to millions of degrees gives off X-rays, which we can detect and study, confirming simulation predictions. Each of these breakthroughs, whether in gravitational wave signatures, frame-dragging effects, or photon rings, brings us nearer to understanding black holes as more than just cosmic sinks. They are complex, dynamic objects that follow patterns predicted by math and confirmed by simulations, giving us models that help to decode some of the universe's most extreme environments. Einstein's field equations may appear theoretical, but they constitute the very basis of our knowledge regarding black holes. They do not merely provide numerical outcomes. They illustrate how space and time are distorted, bent, and stretched under the influence of extreme gravitational forces. These equations are highly complex, consisting of 10 interconnected differential equations that link mass, energy, and the curvature of space-time. When Einstein formulated them in 1915, he probably did not foresee their future uses, but today they are essential for the investigation of black holes. The intricacy of these equations becomes especially clear when scientists apply them to these celestial bodies. Under particular circumstances, the equations forecast that space-time can collapse into a point of infinite density, thereby creating what we now identify as a black hole. Carl Schwarzschild was the first individual to solve these equations for a simplified scenario, a non-rotating, perfectly spherical black hole. This solution, referred to as the Schwarzschild solution, establishes the event horizon and predicts the behavior of light and matter in its proximity. However, actual black holes are rarely so simple. They rotate, engage with their surroundings, and collide with each other, which requires more elaborate solutions and, often, the assistance of computational tools. For rotating black holes, the Kerr solution adds another level of complexity. It explains how a black hole's spin warps space-time, generating a kind of cosmic vortex where space itself is twisted. This phenomenon, called frame dragging, is so immense that it distorts everything in the black hole's vicinity, including light. The equations that describe this rotation are far too complex to be solved manually, so scientists use computers to execute simulations that capture these dynamics in detail. The creation of a black hole simulation is not just about entering numbers into a computer. Each black hole is broken down into a vast number of small elements, similar to a grid placed over space-time. Scientists then compute the gravitational force on each point of this grid, based on the influence of its neighboring points, updating these positions with each tiny fraction of a second. This method is called numerical relativity, where computers are responsible for handling the massive computational work needed to keep up with Einstein's equations in real time. The finite difference method divides the differential equations into small, manageable stages across the grid. Each stage calculates the changes in space-time, enabling scientists to create a time-lapse visualization of the black hole's actions. Another method, known as adaptive mesh refinement, directs computing power to crucial areas like the event horizon. This technique improves accuracy without overwhelming the system, which is vital when dealing with phenomena as complex as black holes. In the case of black hole mergers, simulations need to handle immense gravitational forces. The collision of two black holes is among the most violent events in the cosmos. As they draw closer, they emit gravitational waves, which travel through space-time like ripples in a pond. These simulations must carefully track every twist and turn, showing how the black holes spiral together and eventually merge. After the merger, there is a ring-down phase where space-time vibrates and slowly settles, releasing specific frequencies called quasi-normal modes that scientists can detect with instruments like LIGO and Virgo. The patterns seen in gravitational waves match the predictions from simulations, confirming that we are on the correct path with these models. LIGO's observations of merging black holes in 2015 brought the theory to life, and every new detection refines our comprehension of black hole behavior. Even the recoil, or kick, for merging black holes where the new black hole is pushed away from its original spot has been simulated and observed, giving us insights into how these massive objects interact. Simulating black holes needs enormous computing power. Supercomputers like Blue Waters and Summit carry out billions of calculations per second to recreate the dynamics of black holes. Some simulations can take weeks or even months to complete, with scientists using parallel processing to share the calculations among hundreds or thousands of processors. It is a process that demands a large investment of time, energy, and patience, but the outcomes provide us with a look into the hidden workings of these cosmic giants. Even light acts differently near black holes, and simulations are key to helping us understand these unusual effects. Geodesic tracing, a method that follows the path of light around a black hole, allows scientists to model how photons loop and twist in the black hole's gravitational field. The result is a photon ring, a bright circle around the black hole where light orbits several times before either escaping or being pulled in. This photon ring is what we see in the famous Event Horizon Telescope image of the M87 black hole. The ring itself is not the event horizon. It is light bending around the black hole's gravity, an effect that was predicted by simulations and confirmed by the EHT. The Event Horizon Telescope, EHT, uses a method called interferometry to merge data from telescopes situated around the world. By combining the light from each location, the EHT creates a virtual telescope with a resolution sharp enough to photograph the shadows of black holes. The data is then processed with advanced algorithms to reconstruct the images of black holes, enabling us to see the shadows cast by their event horizons. This visual information matches the predictions from simulations, assisting scientists in verifying their models with real-world observations. However, the simulations do more than just produce images. They also provide other insights, such as how black holes form accretion disks. These swirling rings of gas and dust heat up as they spiral toward the black hole, reaching temperatures of millions of degrees. Simulations indicate that these disks are incredibly turbulent, with particles colliding with one another at high speeds. The energy released from these collisions generates X-rays, which astronomers can detect with space telescopes, offering us a window into the extreme environment around black holes. Simulations also indicate that black holes can release powerful jets of particles that are shot out from their poles at almost the speed of light. These jets are created by magnetic fields that are twisted by the black hole's spin, launching particles out in huge streams. In supermassive black holes, these jets can stretch for thousands of light years, affecting star formation and even shaping entire galaxies. The mathematics that supports these simulations presents special challenges, especially near the singularity, where density becomes infinite. Standard calculations fail in this area, so scientists use methods like excision, where they take out the singularity from the computational grid to prevent undefined values. This workaround lets the simulations concentrate on the event horizon and the nearby regions, where most of the observable effects happen. Coordinate transformations also aid in simplifying the mathematics. By changing how distances and directions are measured, scientists can model black holes using coordinates that make the calculations more manageable. Spherical and polar coordinates are frequently used as they align better with the shape of a black hole than standard grid systems. Each of these adjustments allows the simulation to run more smoothly and precisely, getting us closer to a realistic picture of black hole behavior. The dynamics within a black hole show strange effects, like the warping of the event horizon. Simulations reveal that the event horizons of black holes are not perfectly even. They can develop bulges or twists due to strong gravitational interactions, especially during black hole mergers. These distortions affect the light and matter nearby, bending them in unique ways. As black holes spin, they create frame-dragging effects, twisting space-time around them. This effect, predicted by relativity and confirmed through simulations, is especially strong in fast-spinning black holes. These frame-dragging zones pull in nearby matter, creating a sort of cosmic whirlpool around the black hole. In addition, these models have demonstrated that, much like the tone of an instrument, merging black holes create unique gravitational wave signatures. Scientists can determine the mass and spin of a black hole from gravitational wave data because these frequencies, known as quasi-normal modes, are dependent on mass and spin. It is like deciphering the signature etched in the waves of spacetime. Simulations show that black holes with a high spin can bend spacetime into intricate patterns, influencing how nearby particles move. These revolutions pull material along with them, resulting in a special kind of turbulence in the accretion disk. Matter heated to millions of degrees gives off X-rays that we can detect and investigate, confirming the modeling predictions. Each of these breakthroughs, whether in gravitational wave signatures, frame-dragging effects, or photon rings, brings us closer to understanding black holes as more than just cosmic sinks. They are complex, dynamic objects that follow patterns predicted by math and confirmed by simulations, giving us models that help to decode some of the universe's most extreme environments. Crossing the event horizon of a black hole means entering a place where the normal rules of physics no longer apply. Once you go past that boundary, the gravitational pull is too strong to overcome, pulling you relentlessly toward the center, toward the singularity. Every path, every direction, every possible move leads straight to this central point. It's not a choice. It's an inescapable reality. No matter how powerful you might be, there is no way to escape. In this area, the very idea of time starts to warp and change. An observer watching from a safe distance would see you slowing down as you get closer to the event horizon, your image fading as the light from you is stretched to wavelengths that eventually become invisible. This is because of a phenomenon called gravitational redshift, where light waves are stretched to longer, redder wavelengths by the strong gravitational field. From the observer's point of view, you seem to be frozen, stuck at the edge. But for you, time keeps moving forward, even as the space around you warps beyond all recognition. Within this strange landscape, there is an effect known as spaghettification. This is not just a descriptive term. Spaghettification means that because of the huge difference in gravitational pull between your head and your feet, you would be stretched into a long, thin string, like a piece of spaghetti. In smaller black holes, this stretching happens even before you get to the event horizon. But in supermassive black holes, where the tidal forces near the boundary are not as strong, you could actually cross the event horizon in one piece, feeling the full force of the pull only after going deeper inside. As you get closer to the singularity, the force of gravity gets stronger, and its effects on time and space become even more extreme. Some theories suggest that inside a black hole, space and time swap roles. This means that as you fall inward, moving forward in time literally gets you closer to the singularity. In other words, it becomes your unavoidable future. You can't change your path, turn around, or even stop moving toward the center because time itself is pushing you toward it. The singularity, the very middle of the black hole, is where our current mathematical models start to fail. Density becomes infinite, and the known laws of physics just don't work here. Some scientists think that quantum effects might change this outcome, leading to the formation of a Planck star instead of an infinitely dense point, but this is still unproven. At the singularity, space-time as we know it might not exist. Everything we know about the fabric of reality is broken, which suggests that a new theory, maybe one that combines gravity and quantum mechanics, is needed. Then there is the radical concept that black holes might contain baby universes, separate areas of space-time that branch off from the parent universe. In this model, the matter that is pulled into a black hole could come out as a new universe, existing in a separate space but connected through the black hole. This might sound like science fiction, but mathematically, it's a possibility. Such a universe would exist within the black hole, unreachable from the outside, but with its own separate timeline and laws of physics. Speculations like the wormhole theory suggest that black holes might act as connections to other universes, or even to different areas of our own universe. The math suggests that these connections could be possible, although a safe trip through them would be a whole other issue. Some scientists propose that a firewall might be waiting for anything that goes into a black hole, a high-energy barrier that would destroy matter as it crosses the event horizon, getting rid of any chance of reaching the singularity in one piece. Inside a rotating black hole, things could be even stranger. Instead of a single point, the singularity might form a ring, which would change the structure of the black hole. This ring-shaped singularity creates a space where normal cause and effect no longer apply. Theoretical models predict that a Cauchy horizon could exist here, marking a boundary beyond which the usual rules of physics, like cause leading to effect, no longer hold. The future becomes impossible to predict, leaving open questions about what happens to anything caught inside. Quantum entanglement might even link particles near the event horizon with particles outside, suggesting connections that go beyond the black hole's boundaries. This connection means that even if an object is lost to the black hole, it could still affect particles far beyond it, creating a kind of cosmic bridge that science is just starting to explore. The problem of data retention also comes up. According to classical physics, anything that falls into a black hole is pulled relentlessly toward the singularity and then lost forever. However, according to quantum physics, information cannot be destroyed. The now famous black hole information paradox came from this theoretical conflict. The holographic principle is one of the most surprising concepts to come out of the study of black holes. It suggests that all the information inside a three-dimensional area of space could actually be encoded on its two-dimensional surface, much like a hologram. This idea started with an unusual discovery in the physics of black holes. The amount of information a black hole can hold doesn't depend on its volume, as you might think, but on the area of its event horizon. The physicist Jacob Bekenstein first saw this strange connection in the 1970s, realizing that a black hole's entropy, a measure of disorder or information, was proportional to its surface area. This was a revolutionary discovery because it went against the idea that information should be stored inside a volume, not on a surface. Building on this, Gerard et Hooft proposed that if black holes store information on their surfaces, then maybe our whole universe could work in a similar way. Maybe everything we see, feel, and experience in three-dimensional space is actually encoded on a distant two-dimensional boundary, like a huge cosmic hologram. Leonard Susskind took these ideas even further, turning them into what we now call the holographic principle. He proposed that in a way, reality might just be a detailed projection from information stored on this boundary. This principle has major implications for our understanding of reality, especially when it comes to bringing together quantum mechanics and general relativity. These two fields of physics describe different worlds. Quantum mechanics deals with the tiny subatomic world, while general relativity describes the massive gravitational world. But they don't agree in extreme environments like black holes, where both theories should work. The holographic principle might be the link between them, suggesting that space and time themselves could be emergent rather than fundamental. In other words, space and time might not be as basic as they seem, but could instead come from information on a 2D surface. One of the most interesting parts of the holographic principle is its ability to solve the black hole information paradox. According to quantum mechanics, information can't be lost, but if something falls into a black hole and is eaten by the singularity, where does its information go? The holographic principle suggests that this information doesn't disappear. It could be encoded on the event horizon, saved in some form even if it seems lost inside the black hole. Another important part of this puzzle is the anti-de Sitter conformal field theory, adds a CFT correspondence, a concept created by the physicist Juan Maldatina. ADS CFT shows that a theory of gravity in a higher dimension can be described by a theory without gravity on a lower dimensional boundary. This idea supports the holographic principle by giving a mathematical model for how a 3D space could be fully described by data on a 2D surface. Susskind and others used this model to argue that all information inside a black hole could indeed be represented on its boundary, saving it even if it seems unreachable from within. If the holographic principle is true for black holes, it might also be true for the whole universe. That could mean our three-dimensional experience of reality is just a projection from a boundary we can't see directly. Everything we think of as physical might really be encoded on a distant surface, challenging the most basic ideas about the nature of existence. There's even speculation that dark energy, the mysterious force causing the accelerated expansion of the universe, might be connected to this holographic boundary. Some researchers suggest that interactions with this boundary could affect the universe's energy, possibly explaining why everything is moving apart faster over time. It's an idea that is still very theoretical, but one that adds an interesting dimension to our understanding of cosmic expansion. Experimental evidence that supports the holographic principle is still indirect but interesting. Observations of black hole shadows like the one taken by the Event Horizon Telescope show how light bends near black holes in ways that reflect this projection concept. Advances in particle physics also hint at behaviors that could fit with the holographic view, especially as particles get close to the smallest quantum scales. In experiments at CERN and other particle physics labs, scientists are pushing particles to near-light speeds, exploring the limits where traditional space-time might start to look like a 2D boundary. Perception and awareness are other topics that the holographic principle brings up. What about the way we see things? If reality is really a projection, is our awareness limited to what is written on an unseen surface, limited to what is projected on it? This theory challenges not just our knowledge, but also our interpretation of the world around us. It touches on both physics and philosophy. The holographic principle suggests that what we think of as real might be a thin slice of something bigger, encoded on the very edges of our universe. This idea doesn't just change black hole theory. It forces us to rethink the universe and our place in it, opening doors to questions about existence, perception, and even the nature of reality itself. Quantum mechanics meets black hole theory in a fascinating way. The holographic concept gives a new perspective on the process of data loss inside a black hole. Like a cosmic memory saved on a two-dimensional boundary, it suggests that all the information and particles inside a black hole might be imprinted on its surface. However, quantum theory adds more complexities by showing that particles inside black holes don't act in a normal way. The connection between quantum mechanics and black hole theory is not a smooth one. General relativity, the framework for understanding black holes, works well for large objects and strong gravitational fields. But when we look at the very small, quantum mechanics is in charge. These two areas work under different sets of rules, and when we try to combine them in the context of a black hole, it leads to some confusing contradictions. One of the most famous problems is the black hole information paradox. The paradox comes from a basic rule in quantum mechanics. Information can't be destroyed. Every particle, every bit of matter, has information inside it. But in a black hole, anything that crosses the event horizon seems to disappear, pulled relentlessly toward the singularity. In classical physics, that information would be seen as gone forever. However, this idea doesn't fit with quantum mechanics, where losing information would break fundamental principles. Stephen Hawking's discovery of Hawking radiation in the 1970s made the situation even more complex. Hawking radiation is a result of quantum fluctuations near the event horizon, where pairs of particles briefly appear and one particle falls into the black hole while the other escapes. Over time, these escaping particles make the black hole lose mass and shrink. And eventually, if enough Hawking radiation gets out, the black hole would evaporate completely. But this brings up a key question. If the black hole evaporates, where does the information it swallowed go? Does it disappear with the black hole, or is it saved somehow? Several ideas have been suggested to solve this information paradox. One of them is the holographic principle, which proposes that all the information inside a black hole could actually be stored on its two-dimensional surface, the event horizon. If this is true, it means that everything that goes into a black hole is encoded as information on its surface, saving it even if the black hole eventually evaporates. In this way, information is not lost. It is just encoded in a different form. Leonard Susskind and Gerard 't Hooft were two of the physicists who created this idea, and it has led to a whole new way of thinking about black holes. Another theory, called black hole complementarity, suggests that information could exist both inside the black hole and on the event horizon at the same time. For an outside observer, the information stays on the surface, but for an object falling into the black hole, that information is still there inside. This idea creates a kind of dual reality without breaking the rules of quantum mechanics. Quantum entanglement might also offer a solution. When two particles become entangled, their positions don't matter to how changes to one particle affect the other. Some researchers have suggested that even after hitting a black hole, some particles might stay entangled with those outside the hole, keeping their data connected to the universe beyond. In this way, data stays accessible through an invisible link to the outside world, even if particles fall into a black hole. As for far-out theories, there's the firewall hypothesis. A high-energy wall is said to form at the very edge of the event horizon. In this scenario, to avoid having to explain data inside the black hole, anything that crosses it would be destroyed instantly. Many people believe in the firewall idea, but it goes against some basic physical laws and hasn't gotten much support yet. In looking at what might happen to information in a black hole, scientists have considered theories like loop quantum gravity. This theory suggests that space and time are made of tiny loops, not continuous structures, creating a quantum core inside black holes instead of a singularity. This core could stop matter from collapsing completely, giving a way to save information without breaking quantum rules. Another model, the fuzzball theory from string theory, proposes that black holes might actually be made of tangled strings instead of a singularity, storing information in their structure. But testing these theories is hard. Black holes are very far away and hidden by their event horizons, so seeing their insides directly is impossible. However, scientists can study gravitational waves, ripples in space-time, caused by black hole mergers. When two black holes collide, the waves they make carry information about their properties, and studying these waves helps us understand how black holes interact with space-time on a quantum level. Hawking radiation itself is another problem. It's a slow process. The radiation a black hole gives off is very faint, and for large black holes, it would take longer than the age of the universe for them to evaporate. Detecting Hawking radiation is beyond our current technology, but scientists are working on other ways to explore the effects it predicts. At the smallest scales, space-time may be foamy, filled with tiny fluctuations that change how particles and forces act. This idea of space-time foam suggests that space inside black holes isn't smooth but full of constant tiny changes. Such a structure would mean that particles can't reach infinite density, possibly stopping the formation of a true singularity. If black holes have these fluctuating foam-like structures inside, it could help explain how information is stored and might even hint at a quantum structure of space-time itself. Loop quantum gravity also introduces the idea of a Planck star, a dense core inside black holes where matter reaches maximum compression without collapsing into a singularity. Instead of an infinite density, the Planck star represents a stable state within quantum limits. If true, this model would mean that information is saved in a compact form instead of being lost in an unreachable point. Some theories go even further, suggesting that particles getting close to the black hole's singularity experience a bounce effect, basically rebounding before reaching infinite density. This rebound would stop a total collapse, saving information while keeping the black hole's gravitational pull. The bounce effect is purely theoretical, but it hints at possibilities that might one day change how we understand the deepest parts of black holes. In quantum mechanics, entangled particles can stay linked no matter how far apart they are, bringing up the idea that particles inside a black hole could still be connected to particles outside. This connection could let information leak from inside the black hole in subtle ways, keeping the link with the outside universe and getting around the paradox. Each of these ideas, from entanglement to loop quantum gravity, firewalls to fuzzballs, deals with a small part of the black hole information paradox. And while they don't give all the answers yet, they show how scientists are rethinking the laws of physics to try and understand what happens to matter, energy, and information in a black hole's powerful gravitational field. As we study these mysteries, it's becoming clearer that black holes are more than simple gravitational sinks. They're windows into the fundamental nature of reality, revealing possibilities for how information, time, and space itself might behave at the universe's limits. Cosmic inflation suggests that our universe, once tinier than an atom, expanded at an unbelievable speed in the smallest fraction of a second. Alan Guth first came up with this idea in 1980 to explain why the universe looks so smooth and flat. This quick expansion, or inflation, would stretch space itself, smoothing out any irregularities and explaining why the universe looks so uniform when we see it on a large scale. The question is, why would something expand this fast in the first place? And why did it stop, letting the universe grow at a much slower speed afterward? The theory of cosmic inflation helps to solve what physicists call the horizon problem. Without inflation, distant parts of the universe wouldn't have had time to share light or heat, so we'd expect them to look very different. But they don't. They look almost the same in temperature, which suggests they somehow did interact. Inflation explains this by proposing that those distant parts were once close enough to interact before the quick expansion pulled them far apart. Inflation doesn't just explain why the universe is smooth and even, it also gives insights into why galaxies and other structures formed the way they did. During inflation, tiny quantum fluctuations, small, random changes at the smallest scales, were stretched out into larger patterns. These fluctuations became the seeds for galaxy clusters, creating the structure of the universe we see today. The cosmic microwave background, or CMB, has faint traces of these original patterns, supporting the idea that inflation shaped the early universe. Some scientists suggest that our universe itself could have come from a black hole in a larger universe. According to this idea, what we see as the Big Bang might have been the formation of an event horizon from the point of view of an outside universe. From our perspective, this looked like a quick inflationary period, but it could also look like how a black hole's event horizon grows when it pulls in matter. In this black hole universe view, our universe's boundary could act like an event horizon holding all the information inside it. Just as black holes trap information on their surfaces, the universe might work in a similar way, storing all data about its contents on a cosmic boundary. This fits with the holographic principle, which suggests that everything inside the universe could be a projection from information encoded on its surface. The possibility that inflation is still happening in other parts of the universe is also being thought about by some physicists. This fits into the idea of the eternal inflation theory, which says that the formation of new bubble universes keeps going even after inflation stops in certain places, like our own universe. These bubbles would expand during an inflationary phase, but they would each exist in their own pocket of space. Each bubble universe in this idea might have its origins in a black hole in a parent universe, and ours is just one of many. How might inflation be connected to black holes? Physicists have studied what happens to matter and energy as they get close to a black hole singularity. The huge energy from quantum fluctuations during inflation could be like the conditions near a black hole's event horizon, where space-time stretches and bends. This similarity has led some scientists to wonder if black holes in our universe might make new universes inside them, each starting with its own kind of inflation. Inflation also leaves behind clues in the form of gravitational waves, ripples in space-time caused by massive cosmic events. These waves, found by instruments like LIGO, give indirect evidence of inflation by showing how space reacted to extreme events in the early universe. Primordial gravitational waves made during the inflationary phase could help us understand how inflation works and whether it fits with the black hole universe hypothesis. Finding these waves is hard, but each discovery brings us closer to understanding the forces that shaped our universe. There is also a theory called the Big Bounce, which suggests that our universe's expansion might be part of an endless cycle. In this model, the universe expands, then contracts, only to bounce back in a new Big Bang-like event. Some scientists believe that black holes might have a role in this cycle, with each contraction possibly forming a singularity that leads to a new expansion. If true, black holes could be important not just to our universe's start, but to cycles of creation that may have happened many times before. Understanding inflation also brings up questions about quantum mechanics. During inflation, quantum fluctuations affected everything in the universe. These fluctuations could give insight into how black holes act on a quantum level. In particular, they hint that space-time itself might have a quantum foam at very small scales, with tiny fluctuations constantly shifting and affecting particles. This foam might even stop singularities from forming, limiting the density of matter inside black holes, and possibly offering clues about what started inflation in the first place. Some have suggested that inflation might have been set off by a quantum vacuum state, a condition where energy levels are so low that random fluctuations can lead to sudden, massive expansion. This concept connects directly to black hole physics, where energy fluctuations near an event horizon could drive similar space-time stretching. It suggests that the same principles behind inflation might also explain how black holes affect the space around them. The idea of a baby universe forming inside a black hole also gives a fascinating perspective. According to this theory, when matter and energy go into a black hole, they might compress until they create conditions like the Big Bang. Inside the black hole, a new universe could appear, expanding with its own version of inflation. In this view, each black hole could act as a cosmic seed, creating entire universes with unique properties and laws of physics. The eternal inflation model and black hole universe theories bring up the possibility of a multiverse, a collection of countless universes, each with its own different characteristics. If every black hole leads to a new universe, then the universe we live in might just be one branch in an infinite network of realities. It's a concept that pushes the limits of what we think is possible, suggesting that black holes are not just ends, but also beginnings. One of the hardest questions is figuring out what first caused inflation to start. Seeing or recreating inflationary conditions in a lab is almost impossible because of the extreme energy levels needed. But researchers are getting creative, using mathematical models and simulations to understand what might trigger such quick expansion. We can't see what happens inside black holes directly, and inflationary conditions are far beyond our reach. However, scientists are hopeful that by studying the cosmic microwave background and gravitational waves, they can find clues about the inflationary phase. Each new piece of data could show more about the origins of our universe and, possibly, the role black holes play in creating entire worlds. Inflation, with its roots in quantum fluctuations, black hole dynamics, and the quick growth of space, is still one of the most mysterious parts of the early universe. Dark matter, too, might have surprising connections to black holes. Some scientists suggest that dark matter could be made of primordial black holes, which would have formed in the early universe. Unlike normal black holes that form from collapsed stars, primordial black holes would have formed right after the Big Bang. These black holes would act like dark matter because they have gravity, but don't give off light, acting in ways that are almost the same as dark matter particles. Dark matter and dark energy are two of the biggest mysteries in our universe. Together they make up about 95% of everything, yet they are hidden from our view. Dark matter doesn't give off or absorb light, which makes it invisible, but we know it's there because of its gravitational effects. It's what holds galaxies together, giving the extra gravity needed to keep them from flying apart as they spin. Without dark matter, galaxies would break apart, as visible matter alone doesn't have the gravitational pull to hold them together at the speeds they're moving. One leading theory is that dark matter is made of particles called WIMPs, weakly interacting massive particles. These particles would have mass, giving them gravitational pull, but they don't interact with light or other particles in a way we can see. Experiments all over the world are looking for WIMPs, hoping to catch a glimpse of these hard-to-find particles. Other theories suggest that dark matter might be made of axions, particles so light they act more like waves than particles. Axions would create a kind of invisible fog that wraps around galaxies and helps to hold them together. Another dark matter candidate is the sterile neutrino, a particle that doesn't interact with any other particles except through gravity. These particles could be floating through our universe without us ever knowing, affecting only the mass and structure of galaxies. Some scientists even suggest that dark matter might be coming from extra dimensions, having a gravitational effect from spaces beyond our own, affecting our universe in subtle but powerful ways. Dark energy is a force that's even more mysterious than dark matter. Dark energy makes up about 68% of the universe, and it's the reason galaxies are moving away from each other faster and faster. Unlike gravity, which pulls things together, dark energy acts as a repulsive force, pushing galaxies apart. Scientists found this when they saw distant supernovae and found that galaxies were moving away at accelerating rates, something only a force like dark energy could explain. Some physicists think that dark energy might not be a real substance, but a property of space itself, like a constant background energy. This idea goes back to Einstein's cosmological constant, a term in his equations that represents the fixed amount of energy in empty space. There is also a debate about whether dark energy is constant over time, or if it might change, possibly speeding up or slowing down in the future. According to some hypotheses, dark energy might come from another universe. In this theory, dark energy comes from a higher dimensional space through gravitational leakage from nearby universes. Imagine our universe as a three-dimensional brain floating in a four-dimensional bulk. The force we see as dark energy might really be a result of influences from nearby brains that affect our universe. In this framework, dark energy could be like a pressure from an outside source, pushing outward on our universe. It might even come from interactions at the boundary of our universe, suggesting an edge effect from a multiverse. If true, dark energy would give indirect evidence of extra dimensions and might suggest our universe isn't as separate as we once thought. Black holes might even create dark matter-like effects through interactions with quantum fields. These interactions could increase their gravitational pull, creating areas around them that act like the effects of dark matter. If this is true, it could mean that dark matter might actually be trapped matter from previous cycles of the universe, squeezed into black holes that act as invisible anchors. Some other theories suggest that dark matter and dark energy could be two sides of the same coin. In this view, they would be different forms of an unknown force or particle that works in ways we don't yet understand. The modified Newtonian dynamics, MOND theory, for example, suggests that our understanding of gravity might be wrong. MOND proposes that gravity itself changes at large scales, creating effects that look like dark matter without needing any invisible particles. Others think that dark energy could be a remnant of high-energy processes from the universe's creation. It might be leftover energy from black hole mergers or other strong events, spread across the universe as a kind of background force. This would mean that dark energy is a relic of old cosmic activity, possibly tied to the early stages of black hole formation. Dark matter and dark energy could even represent shadow versions of normal matter and energy, existing in a parallel form that we can't see directly. This shadow matter might interact with our universe only through gravity, creating an invisible structure that holds everything together and drives expansion. Scientists are exploring different ways to find dark matter and dark energy. Detectors on Earth try to catch particles like WIMPs by seeing their rare interactions with normal matter. So far, no definite detections have been made, but each experiment gives valuable data. Observations of galaxy rotation curves also give indirect evidence of dark matter, since galaxies spin faster than visible matter alone can explain. Dark energy effects are measured through redshift, where light from distant galaxies shifts to longer wavelengths as space expands. The cosmic microwave background, the afterglow of the Big Bang, also shows clues about dark matter, as its gravitational pull affects temperature changes across the sky. These mysteries have big implications for the idea that our universe could be like a black hole. If dark energy is affected by an outside universe, it could suggest that our universe acts like a black hole, with expansion driven by interactions with a larger space. The structure of dark matter might hint at our universe's edge, acting like an event horizon, with dark energy pushing outward, much like a black hole's boundary expands as it eats matter. Dark energy's consistent effects across huge distances are like the gravitational pull of a black hole's event horizon, suggesting there may be a deeper connection. Some scientists even think that black holes could be gateways between universes, with dark matter and dark energy giving clues to these connections. The way dark matter is distributed in galaxies is like how matter clusters around black holes, suggesting there may be a link between their origins. It's as if dark matter gathers in patterns that reflect a hidden gravitational structure, much like black holes, shape the space around them. The James Webb Space Telescope and other advanced observatories could show new insights by looking at galaxies and supernovae at extreme distances. Better gravitational wave detectors might also find more about dark matter if primordial black holes are found to make detectable space-time ripples. In labs, scientists are trying to simulate early universe conditions to see if they can recreate the processes that may have led to dark matter and dark energy. Studies of galaxy collisions show how dark matter acts in massive interactions, as dark matter seems less effective than regular matter in these cosmic encounters. Dark matter and dark energy are still mysteries, but each new discovery pulls back the curtain just a bit more. As we learn more, these invisible forces may help us understand not only the structure of our universe, but also its relationship to black holes, higher dimensions, and maybe even other universes. While dark matter and dark energy are unseen forces that shape the cosmos, the event horizon of a black hole gives us a direct boundary to study these puzzles. Just as dark matter creates invisible structures that hold galaxies together and dark energy pushes the universe to expand, black holes hold clues about forces and structures we can't see, but can observe indirectly. Of all the things about black holes, the event horizon is the most mysterious. It's not really a wall or a surface, but it does act as a barrier. At that point, not even light can escape the huge force of gravity, and there's no turning back. For this reason, Black holes look black. We have no idea what's on the inside when we look in. Still, scientists keep their focus on the event horizon because it may give hints about what's happening beyond it. The Event Horizon Telescope, EHT, has let us see something that was once only a theory, the shadow of a black hole. In 2019, it took the first image of the supermassive black hole at the center of the galaxy M87. This image, showing a glowing ring around a dark center, gave a direct look at a black hole's event horizon. The dark spot isn't the black hole itself, but the shadow made by the event horizon blocking light. The bright ring around it is made of hot gas and particles swirling at nearly the speed of light, giving off light that the EHT could see. What makes this image so important is how it confirms predictions from Einstein's general relativity. Light bends around the black hole, creating that special ring as gravity warps the path of photons traveling near the event horizon. This bending of light, called gravitational lensing, is extreme near a black hole, where the gravitational pull distorts space itself. For the EHT to capture this effect at such a distance, it combined data from radio telescopes all over the world, creating a virtual telescope as big as Earth. This huge lens allowed us to see details as small as the event horizon of a black hole, 55 million light-years away. The details in the EHT images go even deeper, showing structures known as photon rings. These rings are made by photons that have orbited the black hole one or more times before getting away, creating multiple layers in the image. Each ring is a little brighter and represents light that has been bent to different degrees by the black hole's gravity. These rings give insight into how information might be layered near the event horizon, suggesting a complex structure instead of a simple edge. The photon rings support theories like the holographic principle, which suggests that everything inside a black hole could be stored on the event horizon, much like a hologram encodes a 3D image on a 2D surface. This concept connects to the idea that the universe itself might have an event horizon, where all the information about our reality is stored on a distant boundary. If black holes work this way, then our entire universe could be structured in a similar way, existing as a kind of projection from this cosmic boundary. Black hole images also help us explore the idea that our universe might act like a black hole's inside. In this theory, the observable universe could be a kind of event horizon within a much larger cosmos. Just as light bends near a black hole, the large-scale structure of space-time in the universe might also lens light because of its mass and shape. This lensing effect would look like what we see around black holes, but on a cosmic scale, suggesting that our universe might be structured in a similar way. A fascinating part of the EHT's findings is the accretion disk, which is a ring of dust and gas that surrounds the event horizon of the black hole. A high-energy zone that makes X-rays and radio waves is formed as particles spiral inward, heating this disk to millions of degrees. By studying these emissions, researchers can learn more about the black hole's feeding habits and the effects they have on their surroundings. Nearby stars and gas are affected by the high energy from accretion disks, which in turn affects the cosmic landscape and the development of galaxies. The behavior of these accretion disks also suggests that black holes might recycle matter. As matter spirals into the black hole, it breaks down under extreme conditions. Some particles are thrown out in jets that shoot out from the black hole's poles at nearly the speed of light, while other particles are pulled into the event horizon. This recycling of matter and energy shows how black holes aren't just cosmic traps. They actively shape their surroundings. The Event Horizon Telescope has made it possible to study these high-energy jets in detail. By looking at the magnetic fields near the event horizon, scientists can see how black holes make these jets and how they affect interstellar space. These jets stretch for thousands of light years, carrying particles and magnetic fields that interact with the galaxy around them. The jets can even affect the rate of star formation, showing that black holes play a key role in galactic ecosystems. As scientists improve imaging techniques, they hope to see these jets in real time and study how they change over time. Future upgrades to the EHT, like adding space-based telescopes, could show even finer details of black holes, helping us understand how different sizes and spins of black holes affect their event horizons. Each new observation could show more about how black holes interact with their environments and how they affect the universe on large scales. Looking at the event horizon also lets scientists test ideas about the information stored around black holes. Since each photon ring in a black hole image has light that has orbited the black hole multiple times, it could carry data about the matter and energy that have gone into the black hole. This layering of photon rings suggests that information might be saved in the light that orbits the event horizon, possibly encoding details about everything that has crossed it. Some researchers think that the event horizon might act as more than just a boundary. It could be a bridge to other universes. In multiverse theories, black holes could act as connections between universes, with information crossing over or even creating new universes in the process. Looking at how photon rings form and interact might help us understand if black holes are connected to other realms or dimensions, giving clues to the largest structure of the multiverse. The EHT's observations have brought us closer to understanding black holes, but they also bring up questions about our universe. If black holes can store information on their event horizons, could our universe itself be a massive storage of information on a cosmic boundary? This possibility fits with theories that suggest our reality might be a hologram, a projection of data encoded on a distant surface. Black hole images, with their complex photon rings and bending light, give a glimpse into how this might work, suggesting that what we see might be only a part of a much larger structure. Each new discovery from the EHT gives fresh evidence about the nature of black holes, hinting at connections to the fundamental structure of the universe. With each observation, we're learning more about how black holes bend, store, and manipulate light and matter, revealing details that could connect to the mysteries of dark matter, dark energy, and even the possibility that our universe functions like the inside of a cosmic black hole. While black hole images help us to explore hidden boundaries in our universe, the idea that our universe itself could be inside a black hole takes this concept even further. This theory suggests that our entire cosmos might exist as the interior of a black hole within a much larger space. Just as light and matter can't escape from a black hole's event horizon, our universe might be similarly bound by a cosmic horizon, a limit beyond which we can't observe or reach. Supporters of this theory point to the structure of our universe as being surprisingly similar to the inside of a black hole. For instance, just as black holes have an event horizon, we have a cosmic horizon, a boundary that limits our view of the universe because light from beyond it has not had enough time to reach us. Inside black holes, space and time are distorted under intense gravity, and our universe also shows signs of space-time curvature on a grand scale. These similarities make it possible to consider that our universe might be an inner region of a much larger black hole structure. One argument for this theory is that the Big Bang might not have been a single starting point. Instead, it could have been the moment when a black hole formed in a higher dimensional space, creating our universe as its interior. This theory proposes that the rapid inflation of space right after the Big Bang might reflect how a black hole's event horizon expands as it pulls in more matter. In other words, the inflation we observe could mirror the stretching effect seen around a black hole. If we really are inside a black hole, it could also help to explain why our universe behaves according to both general relativity and quantum mechanics. These theories often conflict, but within a black hole, they both play crucial roles. The gravitational effects of relativity describe how black holes warp space and time, while quantum mechanics explains the microscopic properties of particles. A black hole-like universe could unify these two perspectives, showing that our reality is shaped by both on different scales. Beyond the event horizon of a black hole, space and time may switch roles. That means time moves forward like space does, with everything inevitably progressing toward the singularity. Some scientists speculate that this swap might explain why time in our universe appears to flow forward toward what we perceive as a future we can't avoid. The holographic principle also aligns with the black hole universe hypothesis. This principle suggests that everything inside a black hole can be represented on its event horizon, like a 3D image encoded on a 2D surface. If this is true, then our entire universe might be encoded on a cosmic boundary, and we are experiencing it as a projected reality from this boundary. Observing black holes gives us a glimpse of how such a structure could work, offering a model that might reflect the nature of our entire universe. Some scientists point to the cosmic microwave background, CMB, as potential evidence. The CMB shows us a snapshot of the universe when it was young and hot, and its smoothness and uniformity could hint that our universe started from a highly compressed state, similar to the conditions inside a black hole. Patterns in the CMB reveal how matter was distributed in these early stages, and studying these patterns may give clues about whether our universe's origins align with a black hole's interior. The speculative side of this theory draws from brane cosmology and string theory. In these models, our universe could be a 3D brane inside a higher dimensional black hole, meaning we are just one layer within a larger multidimensional cosmos. Some theories in string theory, like M theory, even propose that black holes could act as portals to new realms. If black holes create their own inner universes, then each black hole could represent a unique universe with its own physical laws. The bounce theory also supports the black hole universe idea. According to this model, a black hole compresses matter, but instead of collapsing into an infinitely dense singularity, the matter rebounds, creating a new universe in the process. In this view, each black hole could act like a cosmic recycling process, continuously creating new universes from old ones. Of course, there are significant challenges and barriers to proving this hypothesis. We currently lack the ability to observe higher dimensions directly, and the extreme conditions within black holes make it nearly impossible to collect direct data about their interiors. Experimental verification would require technology far beyond what we have, as the energy needed to simulate or observe a black hole's interior exceeds anything we can generate. Critics of the black hole universe theory argue that if we were inside a black hole, we would observe stronger gravitational effects similar to the intense gravity around a black hole's event horizon. Others point out that black holes typically have a singularity at their center, while our universe appears to be isotropic or uniform, with no observable center. This difference in structure raises questions about how a black hole-like model could explain the vast, even distribution of galaxies in our universe. If our universe were inside a black hole, some argue, we should detect signals of an outer boundary like an event horizon. Yet, we don't observe any clear evidence of such a boundary in our cosmic measurements. Others note that black holes cause extreme time dilation near their event horizons, while time in our universe flows at a relatively stable rate without the intense slowing effect expected near a black hole. Testing the black hole universe theory remains difficult due to these limitations. However, future technologies may bring us closer to finding answers. As we build more sensitive gravitational wave detectors, such as those at LIGO, we might detect signals that mimic the conditions inside black holes. Improved AI-driven simulations and quantum computing might also allow us to model black hole interiors in greater detail, providing insights into whether such conditions could match our universe's properties. If this theory holds any truth, the philosophical implications are vast. It suggests that reality as we know it might be a projection from a larger, hidden cosmos. Universes might be nested, with each black hole giving rise to a new reality, and the black holes within our universe could be creating new child universes as well, creating an endless chain of creation. This also connects with simulation theory, where our experience of reality might be just one layer of a more complex, deeper structure. If we are within a black hole, then the creation of our universe wasn't a singular, unique event. Instead, it could be part of an ongoing cosmic process. Rather than a single Big Bang, this model suggests that universes are born repeatedly through the creation of black holes, with each black hole spawning a new cosmos, possibly with its own unique physical laws. While the black hole universe theory remains speculative, it continues to inspire new questions and possibilities about the origins of our cosmos. Observing black holes, analyzing cosmic backgrounds, and advancing technology may someday offer hints about whether our universe is indeed a cosmic interior. As we delve into the possibility of our universe existing within a black hole, it is crucial to acknowledge the pioneering scientists whose theories, experiments, and ideas propelled this concept into mainstream discourse. Their work redefined our comprehension of black holes, expanding their role from mere gravitational sinks to something far more intricate, structures with the potential to generate entire universes. One of the first to explore these ideas was John Archibald Wheeler, a physicist who not only coined the term black hole, but also investigated concepts like quantum foam, where space-time fluctuates at the most minuscule scales. Wheeler's notion that reality emerges from fundamental bits of information, a concept he termed it from bit, suggested that information might be the fundamental building block of our universe. This perspective paved the way for ideas such as the holographic principle, where the information within a black hole could reside on its boundary, hinting that the reality of our own universe might be similarly encoded. Leonard Susskind expanded upon Wheeler's insights with his work on the holographic principle. Susskind proposed that everything occurring inside a black hole could be represented as a projection on its boundary, the event horizon. This idea not only transformed our understanding of black holes, but also implied that the entire universe could be a form of holographic projection, possibly existing within a black hole in a higher dimensional space. Adding to these discussions was Gerard 't Hooft, a Dutch physicist who further developed the holographic principle. His work suggested that information within a black hole is preserved rather than lost, challenging earlier assumptions and lending support to the possibility that the information of our universe might be stored on a boundary, much like in a black hole. Together, the insights of 't Hooft and Susskind strengthened the theory that our universe could be encoded on a larger cosmic surface, Stephen Hawking contributed significantly to these discussions with his discovery of Hawking radiation. This demonstrated that black holes are not merely isolated, unchanging objects. They emit radiation and slowly lose mass over time. Hawking's work on black hole thermodynamics revealed a paradox concerning information loss, leading to debates with Susskind and others on whether black holes destroy information. This question of information preservation became central to understanding whether black holes could create new universes and whether they might function as gateways to alternate realms. In the realm of speculative physics, Nikodem Poplawski proposed that black holes might not lead to singularities, but could instead create new universes. His work is based on the Einstein-Cartan theory, which suggests that the spin of black holes creates a form of torsion that prevents infinite density, potentially causing a rebound effect. Poplawski's idea that each black hole might give birth to a new universe within it aligned closely with the black hole universe hypothesis, providing a mathematical foundation for how such a process might work. Physicist Lee Smolin took these ideas in a new direction with his cosmological natural selection theory, proposing that black holes create new universes with slight variations in their physical laws. Smolin suggested that the universe could function similarly to biological evolution, where black holes produce new cosmos in a kind of natural selection for universes that favor black hole formation. His theory aligns with the idea that black holes could be the seeds for new realities, offering a unique perspective on how our universe might have emerged within a black hole. Roger Penrose offered another perspective with his conformal cyclic cosmology, CCC theory, which proposes that universes cycle endlessly, with each universe beginning where the previous one ends. Though not directly supporting the black hole universe hypothesis, Penrose's work on the cyclical nature of universes suggests that black holes might play a role in this ongoing process, potentially resetting space and time to create new realities. Alan Guth provided an essential piece of the puzzle with his inflation theory, which describes how our universe expanded rapidly after the Big Bang. While Guth didn't directly propose the black hole universe model, his inflationary theory showed how space can stretch dramatically in a short period, resembling how a black hole's event horizon might expand as it consumes matter. This connection between inflation and black holes continues to influence discussions on how our universe's rapid expansion could mirror black hole dynamics. In addition to theoretical work, significant experimental advances have strengthened these concepts. The Event Horizon Telescope, EHT, captured the first-ever image of a black hole's event horizon, confirming predictions from general relativity about how light bends around black holes. By imaging the supermassive black hole in galaxy M87, the EHT provided a real-world example of a boundary where information might be stored, reinforcing holographic theories that suggest our universe could work similarly. The discovery of gravitational waves by the LIGO Observatory also plays into these ideas. Gravitational waves created by black hole collisions carry information about black hole properties that might help us understand if such extreme environments could lead to the formation of new universes. With each detection, scientists gather more data on black hole dynamics, moving us closer to understanding if black holes could be more than just massive gravitational fields. Debates among these scientists have pushed black hole research forward. For example, Hawking and Susskind famously disagreed over the black hole information paradox. Hawking initially believed that information entering a black hole was lost forever, while Susskind argued that information is preserved on the event horizon. This debate ultimately led Hawking to reconsider, supporting the idea that black holes may retain information, which could potentially influence new universe formation. Gerard 't Hooft and Leonard Susskind also had an influential debate on the nature of holography. While both agreed that black holes store information on their boundaries, they differed on how this process worked. 't Hooft's approach leaned toward mathematical models, while Susskind focused on the physical implications, each adding depth to the holographic model and its applications to our universe. These scientific debates have not only expanded our understanding of black holes, but have also influenced broader philosophical questions about reality. The idea that we might live within a black hole challenges traditional concepts of the universe as a single, isolated entity. It suggests that our cosmos could be part of a larger, multi-layered reality, with each black hole potentially creating a new child universe. Some of these theories also connect to simulation theory, where our universe might be a projection or hologram from a deeper reality. If black holes function as boundaries where information is encoded, then our entire universe could be a kind of cosmic simulation, with all physical events unfolding according to data encoded on a larger, hidden surface. The idea that black holes might create new universes also implies that the Big Bang may not have been a unique singular event. Instead, our universe could be part of a cycle where each black hole generates a new cosmos, each with its own distinct physical laws. This model of nested universes suggests an ongoing process of universe creation, with black holes as the engines driving new realms. These contributions by physicists and researchers have led to a new way of looking at black holes, not as cosmic endpoints, but as bridges to unexplored realities. The combination of experimental data, theoretical models, and philosophical insights continues to shape our understanding of black holes. As we can see, the idea that our universe could exist within a black hole has captivated scientists and the public alike. From fascinating scientific contributions to detailed theoretical models, it seems like the pieces might align for a cosmic structure where black holes act as gateways to new realms. However, despite the appeal and elegance of the concept, not everyone in the scientific community is convinced. Numerous challenges and critiques stand in the way, raising tough questions about the hypothesis. For some, the universe inside a black hole model is compelling but falls short under closer scrutiny. So, what are the key obstacles that prevent widespread acceptance of this theory? For starters, there's the issue of direct evidence. Currently, no observations suggest we're within a larger black hole structure. We observe stars, galaxies, and cosmic phenomena, but none of these directly point to the presence of a surrounding black hole boundary. One core argument against the theory is the lack of an observable event horizon. In a black hole, the event horizon is an unmistakable boundary where gravity's pull is so strong that nothing, not even light, can escape. If our universe were inside a black hole, we might expect to see some equivalent of this event horizon. Yet, we don't observe any cosmic structure that behaves like such a boundary. Our universe seems to stretch on, expanding, but with no sign of an outer edge acting as a gravitational barrier. Another challenge is that gravity within our universe doesn't match the intense gravitational effects expected inside a black hole. Near a black hole's event horizon, gravity warps space-time so dramatically that it causes extreme time dilation. Time slows down drastically as you approach the boundary. But in our universe, time flows relatively evenly. This consistency doesn't align with the strong gravitational pull a black hole would impose if we were inside one. the uniform structure of our universe also raises questions. Our universe is isotropic, meaning that matter is spread out uniformly in all directions. Black holes, on the other hand, are not known for such smoothness. Matter inside them would be drawn toward the center rather than remaining evenly spread out. This contrast between our universe's even distribution of matter and the chaotic interior we'd expect inside a black hole creates a fundamental difference that's hard to overlook. One of the most direct challenges comes from the absence of a singularity. In a typical black hole, gravity pulls all matter inward toward a central singularity, a point of infinite density. But our universe doesn't have a discernible center or a single focal point where all matter is drawn. We observe a vast, expanding universe with no obvious center, which is difficult to reconcile with the structure of a black hole. Critics also point to the inconsistencies in expansion rates. Our universe has been expanding at an accelerating rate, driven by dark energy. However, this rate of expansion doesn't match the predicted growth rate of a black hole's event horizon. If we were inside a black hole, we might expect to see a different pattern of growth, one that mirrors how black holes behave as they consume more mass. Yet, the acceleration we observe appears to contradict the expected behavior inside a black hole. Speaking of dark energy, its role complicates things further. Dark energy drives the expansion of the universe, pushing galaxies apart. Inside a black hole, gravity reigns supreme, pulling everything inward toward the center. So the existence of a force that actively pushes space apart is difficult to reconcile with the idea that we're within a black hole, where we'd expect gravity, not a repulsive force, to be dominant. The differences between the Big Bang and a black hole singularity add to the skepticism. The Big Bang is understood as a rapid expansion from an incredibly dense and hot state, whereas black hole singularities pull matter inward, compressing it toward a point. If our universe came from a black hole, it's unclear how this shift from compression to expansion would occur. The Big Bang and a black hole singularity are fundamentally different in nature, creating another gap in the theory. Hawking radiation poses another challenge. Black holes slowly lose mass over time as they emit Hawking radiation, eventually shrinking as they release energy. If our universe were inside a black hole, we might expect some similar kind of energy loss or an indication that our universe's boundaries are slowly shrinking. However, our universe is expanding with no sign of energy loss from a boundary, suggesting we might not be within a black hole. Then there's the paradox of size. Our universe is vast, stretching billions of light years across, while black holes are much more compact. The scale of our observable universe seems incompatible with what we'd expect if it were confined within a black hole. This size paradox presents a fundamental mismatch between the structure of black holes and the scale of our universe. From a theoretical standpoint, general relativity presents issues when applied on such large scales. While general relativity explains gravity well on cosmic scales, it doesn't imply that expanding universes could exist within black hole boundaries. Quantum mechanics, too, presents problems, as it doesn't naturally align with the black hole universe model, particularly around the preservation of quantum information across such a vast space. The theory also faces challenges around extra dimensions. Hypotheses that place our universe in a higher dimensional black hole remain speculative, as we have no way to observe or interact with these extra dimensions. Without direct evidence of higher dimensions, the idea of a universe within a larger black hole remains theoretical, and without empirical support, it's difficult to fully accept. The entropy paradox is another point of contention. Black holes are thought to increase in entropy over time, which is a measure of disorder or information. But our universe also has its own entropy, which grows as it expands. The parallel growth of these entropies, one within the black hole and one within our universe, creates a complex question. How can two entropic systems coexist if one is inside the other? Critics also argue that alternative explanations for inflation weaken the need for a black hole model to explain our universe's expansion. Inflationary theories provide a well-supported explanation for why the universe expanded rapidly in its early moments, and these models don't require a black hole framework. Without a clear necessity for a black hole to explain inflation, some see it as an unnecessary complication. And then there's the issue of cosmic horizons. In the black hole universe hypothesis, cosmic horizons might be seen as the boundaries of a black hole. But cosmic horizons are simply limits set by the speed of light and the age of the universe. These horizons don't necessarily point to an outer event horizon, but rather represent the limits of what we can observe based on light's travel time. Philosophically, the idea of nested universes within black holes creates paradoxes. If every black hole produces a universe, then an infinite number of nested universes would form within each other, a concept that feels both untestable and endless. This infinite nesting of universes raises philosophical questions that blur the lines between science and speculation, complicating the theory even further. Many scientists argue that the theory lacks clear, testable predictions. Science relies on falsifiability, the idea that theories must make predictions that can be tested and potentially disproven. The black hole universe hypothesis struggles with this, as it doesn't provide clear ways to test or disprove it. Without testable predictions, it remains a largely speculative concept with limited potential for empirical verification. Each of these critiques highlights the complexities and gaps in the black hole universe hypothesis. While it's a fascinating idea, significant obstacles remain. The scientific community continues to question the feasibility of this model, pointing to everything from gravity and expansion to entropy and dark energy. After examining the scientific critiques of the black hole universe hypothesis, we are left with questions that extend beyond the realms of physics and mathematics. If our universe truly does reside within a black hole, the implications touch upon profound questions of existence, perception, and the very nature of reality itself. In some ways, this theory reshapes our understanding of what it means to exist, as well as our place in a much larger, possibly layered, cosmos. If our universe is contained within a black hole, it suggests that we are bound by limits we cannot perceive or escape. This challenges the nature of reality, hinting that what we experience might be a mere slice of a much greater whole, an illusion of space and time created by the structure of the black hole. According to the holographic principle, everything we experience in our three-dimensional world could actually be a projection of information stored on a two-dimensional surface. This would mean that depth, distance, and even time might not be as fundamental as they appear, but are more like the result of data encoded on a distant cosmic boundary. It's a bit like watching a flat movie screen that somehow conveys the illusion of three-dimensional space. We might be living in such a projection, making us part of a reality that's limited and defined by the boundaries of the black hole containing us. This leads to questions about human perception. If we're inside a black hole, our senses and instruments are bound by the cosmic horizon, essentially a limit beyond which we cannot see or measure. In a way, this parallels our own experience of physical and mental boundaries. Just as we can't observe beyond the cosmic horizon, Our minds struggle to perceive anything beyond what our senses can process or what our current understanding of the universe allows. The limits of human perception might reflect the physical limits imposed by our supposed black hole boundary, raising the possibility that everything we know is only a fragment of a much larger structure that we cannot fully access. Thinking about the universe within a black hole also shifts our understanding of existence. If every black hole leads to a new universe, then our universe might just be one bubble in a vast multiverse, with countless other bubble universes existing in black holes across a higher dimensional space. This view would imply that life and existence are not unique to our universe, but may arise repeatedly, with different forms of life developing under different laws of physics in each universe. Our sense of being special would shift as our universe becomes just one small part of an endless cycle of universe creation. This also connects to the nature of consciousness. If the universe is a projection, then consciousness itself might be an emergent property, something that arises from encoded information. Our awareness, thoughts, and perceptions could be the result of complex information interactions at a cosmic boundary, making consciousness not a separate entity, but something woven into the structure of this universe. This view brings up philosophical debates about free will. If reality itself is encoded and projected, is everything in the universe predetermined by this cosmic encoding, or do we somehow exert independent will within these encoded limits? Could free will exist in a system where the fundamental laws and behaviors are potentially set by information encoded on a boundary we cannot alter? Our understanding of self and scale also changes. Humanity has long perceived itself as the center of existence, but the idea of a black hole universe places us within a cosmic hierarchy where our universe might be one layer in a complex, nested structure of realities. This changes how we see ourselves, moving us from a central position to being part of a vast, layered system. Recognizing this hierarchy redefines our importance as we become a part of an intricate cosmos that might be layered with universes created in other black holes, each with its own unique structure and purpose. Living inside a black hole also brings up the intriguing overlap with simulation theory. If the universe is a projection from a two-dimensional surface, it starts to resemble the concept of a simulation, where our reality is a representation of encoded information. Just as a computer program creates an artificial environment that seems real to its inhabitants, our universe might be an elaborate simulation created by the fundamental laws and encoded data on a black hole's event horizon. This perspective challenges the realness of our experiences, suggesting that what we perceive may be as much a construct as the virtual worlds we can create with our own technology. And if our universe is projected from a black hole, what does that mean for the nature of life and death? If consciousness and physical existence are tied to information within a boundary, then perhaps life and death are simply transitions between different states of information. Consciousness may not end with physical death, but could be part of an ongoing cycle of information that exists in this projected space, altering our perception of mortality. The idea that boundaries could encode all cosmic information hints that life might transcend individual existence, becoming part of a vast network of information that continues beyond what we can currently observe or measure. The concept of interconnectedness grows stronger when we think about cosmic boundaries. If all information about the universe is contained on this boundary, then everything within the universe might be interconnected in ways we can't yet understand. Human consciousness, in this view, may not be an isolated experience, but could be part of a larger, universal consciousness, connected across space through the encoded information on a cosmic boundary. If we are indeed within a black hole, what purpose does human life hold? Are we here by random chance, or is there a broader reason for our existence within this cosmic structure? Some might see this as a call to find purpose in exploration, in understanding the universe we're part of, and in pushing the boundaries of human knowledge. Others might view it as a reason to focus inward, as the cosmic perspective shows us that individual lives are part of a larger system. Purpose might not be inherent, but could be something we create in response to our place in the universe. Time itself becomes a fascinating concept when viewed through this lens. If space and time are projected, then time might be an illusion created by the encoding process on the boundary. Our experience of time flowing forward might be a result of the way information is structured in this universe. This challenges our understanding of time as a linear progression and raises questions about whether the past, present, and future are simply constructs within a larger, timeless boundary. Thinking about consciousness in this way also brings up ideas of collective awareness. If all beings in the universe are part of a single projected reality, then each individual consciousness might be a fragment of a larger, universal consciousness. In this sense, human awareness could be the universe's way of observing itself, a self-reflective property that allows the cosmos to gain awareness through the conscious experiences of its inhabitants. All knowledge will be constrained by the confines of this cosmic structure if we are indeed living within a black hole. We may be blind to certain realities because our perceptions are constrained by the projections of this reality. While this doesn't discount the importance of knowing, it does highlight the boundless potential for discovery as we test the limits of our understanding, cognizant that there may be more out there waiting to be discovered. Each of these ideas reshapes our understanding of what it means to be alive, to think, and to exist. It challenges the line between reality and perception, pushing us to consider the possibilities that lie beyond what we can currently measure or observe. In this vast and complex picture, we're left with profound questions about the nature of self, existence, and our place in the cosmos. As we can see in the exploration of our potential existence within a black hole, science has offered compelling insights. To test these ideas, we need tools that can observe and measure black holes like never before. Future advancements, both in observational technology and theoretical models, are setting the stage for deeper investigations into these mysteries. The upcoming upgrades to the Event Horizon Telescope, known as the Next Generation EHT, EHT, represent a key step forward. This upgrade aims to capture even sharper images of black hole event horizons, allowing us to observe how light behaves in extreme gravitational fields with unprecedented detail. By revealing more about the structure and behavior of black hole boundaries, the EHT could help us understand the nature of the very horizon that might define our universe. In addition to ground-based telescopes, new space observatories like the James Webb Space Telescope, JWST, and the upcoming Lynx X-ray Observatory will let us peer into supermassive black holes at the centers of distant galaxies, examining how these giants formed and evolved in the early universe. If our universe is indeed contained within a black hole, then studying these supermassive black holes might offer clues about how structures like ours could come to be. The European Extremely Large Telescope and the 30-meter telescope will also focus on high-resolution imaging of black holes, providing an even closer look at the intense environments near event horizons. Gravitational wave observatories are another major development. LISA, or the Laser Interferometer Space Antenna, will be a space-based detector designed to capture low-frequency gravitational waves. This observatory could detect waves from massive black hole mergers across vast distances, giving us data on black hole interactions that lie outside the range of current ground-based detectors. As more gravitational wave observatories come online, like the Einstein Telescope and Cosmic Explorer, we'll be able to map black hole events more accurately and observe cosmic-scale mergers, possibly detecting patterns that align with the idea of a black hole universe. Beyond observing black holes directly, we are also venturing into the realm of quantum physics and high-energy experiments to understand the inner workings of black holes. The Large Hadron Collider, LHC, along with its upcoming high-luminosity upgrade, might provide insights into particle interactions at energy scales that mimic black hole environments. For example, some theories suggest that micro-black holes, or analogs of black hole event horizons, could emerge under the extreme conditions created by the LHC. If this happens, we could observe black hole-like behaviors in the lab and study their properties directly. Future particle accelerators, like the Future Circular Collider, FCC, or a potential muon collider, could push these experiments even further. With these machines, scientists hope to explore interactions at even higher energies, bringing us closer to understanding how matter and gravity behave near black hole thresholds. Experiments using ultra-cold atoms or intense lasers are even creating tabletop black holes, miniaturized environments that mirror certain black hole properties, allowing us to study phenomena like Hawking radiation and quantum entanglement on a small scale. These analog systems could give us new perspectives on the nature of black holes and the boundaries that might define our universe. As we build more sophisticated technology to observe and simulate black holes, artificial intelligence, AI, is becoming an essential part of the process. AI's ability to analyze massive data sets has already proven useful in black hole imaging. It was AI algorithms that helped process the data from the original Event Horizon Telescope to produce the first image of a black hole. Moving forward, AI will play an even larger role. For example, AI-based simulations of black hole mergers can now model these complex processes in real time, revealing the subtle gravitational waves produced by these events and showing us how space-time distorts and warps during a merger. Machine learning, a subset of AI, also helps with detecting and analyzing gravitational wave signals. Gravitational wave observatories generate enormous amounts of data, but only a tiny fraction of that data actually contains meaningful information. AI is helping to sift through this noise to identify signals from black hole mergers and other cosmic events, potentially uncovering fainter signals that were previously overlooked. Some neural networks are even being trained to predict black hole mass and size based on galaxy data, making it easier to estimate black hole properties where direct measurements aren't possible. AI might also help us unravel the black hole information paradox, one of the biggest puzzles in theoretical physics. The paradox revolves around whether or not information that falls into a black hole is preserved or lost forever. By using AI to process quantum information near black holes, researchers hope to gain new insights into how information behaves around these cosmic giants, which could be key to understanding whether information is ultimately lost or somehow encoded on the event horizon. In cosmology, AI has another fascinating role, analyzing the cosmic microwave background, CMB. Machine learning algorithms can detect faint patterns in the CMB, the leftover radiation from the Big Bang. Some of these patterns might reveal connections to primordial black holes or early black hole formation, potentially offering clues that align with the black hole universe hypothesis. Theoretical breakthroughs are also on the horizon. Researchers are developing new simulations of universe formation within black holes, testing models that might explain how a universe could emerge within a black hole singularity. High-performance computing allows scientists to simulate complex black hole environments and test different scenarios, like the expansion of space-time within a black hole or the role of higher dimensional spaces. String theory and loop quantum gravity are two areas that might provide breakthroughs in our understanding of black hole physics. String theory, which proposes that fundamental particles are one-dimensional strings, could help to explain black hole singularities, suggesting they might be gateways to other realms. Loop quantum gravity, on the other hand, seeks to unite general relativity and quantum mechanics by proposing a granular nature of space and time. Both theories offer insights into how black holes might behave at their cores, and, if validated, they could reveal new layers to the black hole universe hypothesis. Even with all the groundbreaking research and incredible theory surrounding black holes, some of the most essential questions about them and the origins of our universe remain unanswered. Could our universe truly be contained within a black hole? If so, what does that mean for our understanding of reality, existence, and everything beyond the boundaries we currently observe? The black hole universe hypothesis invites us to rethink everything we know, but with our present tools and knowledge, we're only scratching the surface. The biggest mystery is what actually happens beyond the event horizon. We have detailed models and theories, but without direct observation, we're left with many unknowns. Is a black hole singularity a true endpoint, or is it the doorway to another universe just like ours? The idea that black holes might be seeds for new universes suggests that what we call a singularity might be where a new realm begins. But without the ability to peer inside a black hole, this remains purely hypothetical. Then there's the question of information preservation, the heart of the black hole information paradox. Hawking's work on black hole radiation suggests that black holes slowly evaporate, but where does the information that falls into them go? If information truly disappears, it could mean our fundamental understanding of quantum mechanics is incomplete. If, however, information is preserved, it could support the holographic principle, implying that everything inside the black hole, including potentially our universe, exists as information encoded on the event horizon. Dark matter and dark energy also remain perplexing, with possible connections to black holes yet to be fully explored. Dark matter seems to cluster around galaxies and interact with black holes, while dark energy drives the universe's expansion. Could these phenomena be influenced by forces outside our universe, linked to a larger cosmic structure? Or are they remnants of black hole dynamics, leftover forces from beyond the event horizon? As a last philosophical consideration, what does it imply if we are actually within a black hole? Does it alter our perception of the cosmos, our purpose in life, and the significance we ascribe to things? Although existential concerns have always plagued humanity, the prospect that our cosmos is part of a vaster cosmic system deepens these contemplations. It suggests that we could be a part of something far larger, something that our understanding of is just scratching the surface of. The future of black hole research promises even more discoveries and perhaps answers. I hope you enjoyed the video. If you did, feel free to subscribe to the channel. Thank you.